So, yeah, thank you for coming. And yeah, so right-hand rule number 3. It's probably the central thing of magnetism, or at least the early part of it. Right-hand rule. Rule number 3. Okay, so right-hand rule number 3. So, in essence, moving charge experiences a force in a magnetic field. So this gives the direction of the force on moving charge. So this gives the direction of the force on a moving charge in a magnetic field. Okay, so do you remember me mentioning that only moving charge experiences a force? Yes? Okay, like if I have an electron sitting in a magnetic field placed there, it experiences no force because it is not moving. Yes? I went over, excuse me, I went over in one lesson why it experiences a force, and it's to do with special relativity and length contraction. That is not a core thing in the high school conception of magnetic fields, okay? Even though in reality it's central. We don't really, we in high school we sort of learn rules of thumb with magnetic fields, like, okay, this is the way it pushes in this case, and here's and how much the force is. And we don't as much concentrate on the why, because the why is quite high level. So this is a rule of thumb to recognize which way the force is. Okay, so so here it is. Now, if you have a, let's see here, arrow. Okay, so if you have a charge which is moving, say, that way, and the magnetic field is that way. So I'll label that as B and V. And if it is a, let's see, if it is a negative charge that's moving, because it matters whether it's positive or negative, then if it's positive, the force is going like literally the other direction. Okay, so if it is negative, then we use the right-hand rule to find the direction of the force. So here's the rule. So flat hand, flat right hand. So flat right hand, okay. Fingers in direction of B. Of B. The thumb points in the direction of V. So thumb in the direction of V. And here's the weird part. Okay. If it is a positive charge, the force is normal to the palm, perpendicular to the palm. The force is out of the palm. So if it is a positive charge, the force comes out of the palm. Okay. If it is a negative charge, the force comes out of the knuckle. So this gives you sort of a memory mnemonic, like a little chant, as it were. Positive palm, negative knuckle. Okay, PP. Yeah. So if we imagine this, if we're looking at that, if we're looking at the screen, okay, so with the screen, the fingers point that way. The thumb points in the direction of the velocity. Yeah, so the thumb points in the direction of the velocity. And if it's a negative charge, the force comes out of the knuckle. Therefore, the force is into the page. See, the force is into the page. And then we write a vector for going in that goes into the page as an x, right? So, we draw a little circle, and then we put an x there. Okay, and that's the force. Yes? If it was a positive charge in the same situation, the force would be out of the page. Yes? Okay, cool. And of course, we all remember, the way you write a vector into the page is with an x, is in the feathers of an arrow, and the dot is the pointy end of an arrow, which means out of the page. Okay? So cool. So the way we learn this is just, we'll try a couple exercises for this, okay? So I'm going to teach the lesson more with me. I'm not going to interact with the screen. I'm going to see if I can do this with just staying in this frame here, okay? Because the problem is if I'm standing over by the screen, I'm poorly lit.
Oh yeah, it's
right. Yeah, so I'm going to use that camera. Okay, so here are the exercises. This is going through a few of these usually makes the right-hand rule stick. Okay. But I should say this as well. This right-hand rule, it's not the only right-hand rule. There are right-hand rules which are like 3 fingers like this, and you'll probably see that more in university when they're doing something called the cross product, the vector cross products. And this is actually, yes, it is. It is. I mentioned it on the previous lessons. But this right-hand rule is specifically useful for electrostatics, and especially in high school type problems. And I find that it's very memorable. The positive palm, negative knuckle thing, it's really easy to remember. So much so that I didn't do physics for a while, and when I started to tutor physics, it just popped right into my brain after all that time, after years and years. So if it stays in my brain for years and years, it's probably a good mnemonic, right? So that's why I teach it. And it's quite clear, right? Flat hand. Okay. Class, all one of you? Okay, find the missing vector. Okay, so number 1. Okay. VB, and why don't we say it's negative, and then 2. And positive 3. F V positive 4. Yeah, how about that? V, no. B, F, negative, and then 5. F, B, okay, and then 6. So with these, we do not want to contort our hands to cause any pain, so keep that in mind, with especially this one. So nothing should cause pain here. So don't do anything that hurts. B, V, okay. Oh yes, 5 and 6. Positive, negative, how about we say negative, and then positive. Cool, thank you. Let's plug my computer in here. It's a trick it's a trick we teachers use. You ask a question that doesn't truly have an answer, and it causes, well, it does have an answer, but it's a strange one. It causes perplexity, which triggers learning. Okay. So I put this on manual focus now, so hopefully it's on focus on my face right here. Okay, so, all right. So the first one, okay. So the first one is fingers to the right, or fingers this way, thumb down, and then the force is out of the knuckle. Yes. So it's out of the page. So circle, out of the page, force. Yes. The next one would be fingers up, thumb to the your left, and then positive charge. So it's, of course, into the page, right?
Yeah.
Okay. So the force is into the page. F. The third one is, okay, so you're given the force, but it's positive, right? So the force is to your left, so the force is like this way. The thumb is down, yes? So thus the magnetic field is out of the page. Very good. So that's B. Number 5, or 4, I mean. Contortion. Okay, so thumb, so the negative. So the knuckles are out of the page, and then the fingers are down. Yes? So the force, the velocity is that way. Like to your right, yes? To your right? Okay. Yeah. You all agree? You agree? Yeah. Okay.
Yep.
Cool. Then for number 5, okay, the force on a negative charge, the knuckles are to your right. The fingers go into the page, so the velocity is up. Very good. So the velocity is that way. Yes. Now, as for number 6, number 6, there is no direction implied because the force is 0. It's 0 force because the velocity and the magnetic field are parallel, right? So there's no force. No force. All right, because B and V are parallel. Okay.
Wait, so that means like a particle's magnetic field is that way?
Yeah.
Like it's moving that way. That means it has no.
No force from them. No force from the magnetic field. Yeah.
So it doesn't matter if it's positive or negative. It
Doesn't matter. It's 0 force. Yeah. I could mention that this is based on something called the vector cross product. You didn't see that lesson, or did you?
I just looked like just now, but
Okay.
I didn't look really deep into it.
Okay. Well, yeah, it's the formula for the force is this FB. This is the university version of the formula, which is using something called a cross product, which is something I can't fully teach you in the context of high school. But it is this. It's Q and then q being a charge, and you plug the charge in, and then the velocity vector cross the magnetic field vector. Okay, QVB.
What do you mean by cross?
Yes, exactly. That's something I haven't taught you in high school. The cross product is a one of the two ways we can multiply vectors by one another. You have previously learned the dot product.
Yeah, the dot.
Yes, good. I'm glad you remember, which we sometimes call the scalar product. And the scalar product,
Small.
yeah, it just gives a positive or negative number. It gives a scalar. It gives a scalar. So that's why we call it the scalar product. And we use that for finding work, like the work done by force, if you'll remember. Yes. So work is the scalar product of the force and displacement vectors. The cross product is different.
So do you need to like work out the vectors in addition to
Yeah, the result is a vector. The best way I could explain it to you would be this, I suppose. If we were just going like this, like if we were just going like C is equal to A cross B. That's pretty messy. A cross B. Okay? So if we imagine we had C is equal to A cross B, and we wanted to conceptualize or calculate what C was, and you're given A and B vectors, okay? So imagine that you have two vectors, just one and then two, like A and B. And they are here and there, yes? Okay, so what we do with a cross product is, and these are vectors we imagine that they're pointing in 3 dimensions. Okay, so they're,
Wait, so 3 dimensions?
what? 3 dimensions, yeah. So this is supposed to be 3 dimensions. So to bring it into the 3rd dimension, imagine my arms are vectors.
Oh.
Okay.
Okay.
All right. So can you picture this is like A and B? Okay. All right. And so I want you to picture that these 3 vectors, these 2 vectors, I mean, they span a plane. They imply a plane, like a sheet.
X, Y, Z?
Yeah, but it's a 2-dimensional plane in 3 dimensions. It's tilted. See, I can actually move my hand over the plane. Feel it? See? There's the plane. Right? You see? It's defined by these 2 vectors. It's actually something called the vector space, but we won't get into that right now. Okay? But this is a plane, yes? Does that make sense?
Yeah.
Okay? Okay. C is perpendicular to that plane. Like out of the plane, normal to that plane.
Wait, but these 2 planes are different.
No, there's one plane.
Oh, that cross.
Yeah, see, this is one plane. One plane. Big sheet. It extends out beyond the vectors. One plane. Yes, I'm moving my hand over that plane right now. Yes? And then goes off like that, all different directions. Yes? Okay? So we can imagine being normal to the plane, right? Like this. Or that way.
Yeah. Wait, so what you mean by plane? Is
Yeah.
it like, so like if it's like 2 vectors
Yeah.
like this, so what you mean by plane? Is
Yeah.
it like X in this direction and Y in this direction?
It doesn't have to be.
Or Y in this direction?
It doesn't have to be. I mean, we're working in 3 dimensions. So you could still have this plane old up, X, Y, Z, horizontal, vertical, and then you could tilt the plane. So the plane is tilted. You haven't seen much like this in high school. Yes? But that's probably one of the big differences between high school physics and university physics. Obviously calculus in first year of physics. But the other thing is you're doing a lot of your stuff in university in 3 dimensions. So it's a lot of the same ideas you did in high school, but adding a 3rd dimension,
Yeah.
right? I didn't actually find first year physics that bad.
Oh, really?
Physics only gets really strange, I think, in 3rd year.
Yeah,
Oh, now special relativity you can do in a second here. It's general relativity is the hard one, but you barely even general relativity is kind of like a fourth year honors degree course or grad school. General relativity is utterly brutal. Um, so yeah, but no, but it starts to get weird. Physics starts to get weird in third year when you start doing quantum mechanics seriously, and when you start doing electromagnetism seriously, right?
So like a more deep, much deeper.
Much deeper, much deeper, like line integrals, and yeah. Yeah, but when you get there, you're ready, right? Obviously, you're looking up at the top of the mountain. I'm not going to be up there. Well, when you're just below the peak,
Okay.
right? You just do it step by step, right? Yes, step by step. But here, I'll draw C. So C will either be either here or here. If you can picture the dimensions, right? And where C is depends on the order that you cross product them. Like if you're going A cross B or B cross A is different.
Oh, so it's like opposite.
Mm-hmm. So there's C or C. Or whether there's a negative in front of it, right? Okay. And I mentioned the university right-hand rule. As I remember, the right-hand rule in university is for cross product, and it uses the three fingers.
Oh, so like in that way it's like three-dimensional.
Yeah. You see, you have three.
Yeah.
Yeah, and this gives the right-hand rule, like the direction of the cross product. That's one way to get the direction of the cross product. So you just wait when you get there, and you'll be fine. Okay.
So for this one, if it's like A cross B,
Yeah.
which direction would it be? Because like
Yeah, you embarrass me that I've forgotten the I've forgotten the actual order. To be honest, I've actually I know that there is a right-hand rule, but I just have to look it up. So it's just something I haven't. I probably should just look it up. But yeah, I say it for vagueness, one or the other for now. Okay.
So it does matter for the order.
Oh yes, it does. There is a specific answer.
Okay.
Yeah, and yeah, I probably should just not be so lazy and look it up, but I don't use it in high school, so. And that's why we have this one too, right? This is basically the cross product as well. If you think about it, right? Like, because your hand is the plane.
Oh wait, yeah, it's still three-dimensional.
Yes, it is, but it's very visual. I love this right-hand rule because this is the plane that I'm describing with the cross product, right?
Yeah, and then like the normal.
Yeah, normal to.
Yeah.
Yes, you see, right? And then if it's positive, it's this way,
Mm-hmm.
and if it's negative, it's this way.
Yeah.
Yep.
Okay.
Okay. So let me think about that. So V cross B, A cross B. So let's see. I'm just trying to picture this. V cross B. I don't want to commit myself. I think I know which one, but I don't want to get it wrong. Okay. So yeah. So there it is. So that's the cross product. Yes. And yeah. So the high school version is this. This is the cross product in more high school accessible idea, in a more accessible way. Whoops. My mouse, okay. Computer is not scrolling there. There we go. Okay. So here's the high school version. Or at least advanced high school. It's in magnitudes. So the magnitude of the force is equal to the magnitude of the charge multiplied by the magnitude of the magnetic field vector multiplied by the magnitude of the velocity times sine of theta, where theta is the angle between V and B.
Wait, so here is multiplying, right? Just straight up.
Yes, straight up normal multiplication. And I know I've gone over magnitudes in the past with you when I did the scalar product, right? So it's the angle between B and V. And then to further simplify in high school, okay, I'll show you where theta is in the diagram. So theta, in terms of A and B, would be like there, right? That's the angle between the two.
And it's like three-dimensional.
Yes, in the plane. Good. It sounds like you're grasping this. That's cool. So, excuse me. Then, and obviously B and V, these are the magnitudes, like just the lengths of the vectors. And for high school, we typically say that theta is 90 degrees. So we assume that they are perpendicular to one another already. So we usually assume that theta is 90 degrees.
So it's like a year calculate.
Yeah, in high school. And if that is the case, then we often write this. FB is equal to QVB. And then the direction of said force comes from the right-hand rule. And these are assumed to be magnitudes, even though I don't write the absolute value. Yes? So that, yeah.
For the FB here,
Yeah.
is it, so it is a scalar product, or is it a?
Oh, it's not really, because a scalar product is of two vectors multiplied to produce a scalar. These are all scalars because they're magnitudes, you see. Yeah, so that's a good point. Yeah, so that's what we typically get in high school. And of course, you know, it is so because sine of 90 is 1.
Yeah.
Yes. This also brings up the other thing I mentioned in question 6 on the class problem I gave you just now, where the vectors are parallel, right? That means theta is equal to 0 when they're parallel. So that means theta equals 0. Oops. Handwrite something that I didn't say. There we go. Theta equals 0, and therefore FB equals 0 as well, because sine of 0 is 0. Right? So there's no force when they're parallel. And geometrically, it makes sense that when they are parallel, there is no force implied. Because if you think about it, if they're parallel, there is no longer a spanned plane. Right? It's just a line. Yeah? So you can't infer a perpendicular. You can't infer a perpendicular vector anymore. Perpendicular to what plane? There's just like there's infinitely many planes rotating around a line. You can't pick one, right? But as soon as they are off a little bit, then you have the plane or the vector space. Yes, cool. Yeah, there was something I was going to say. Yeah, that's one. Yeah. And yeah, so because of this direction, if you fire a charged particle into a magnetic field in the right direction, it'll travel in a circle. It'll travel in a circle because the force would be perpendicular to the velocity always. I can show you. Okay. But I'm running out of time, and I suspect my camera is going to be full very soon because this is a limitation right now of this. I'm working out bugs for recording lessons, so.
So, do you export it to a computer like right after so that I
Yeah.
can?
Well, yeah, I have to actually edit it together. So I've got a 2 terabyte little hard drive, and I just put them all in folders, and then I mix them together with Final Cut Pro, and then I make an output video.
Oh, so it takes like a long. It sounds like it takes a long time.
It's not that bad with Final Cut. The rendering, though, can take a couple hours maybe, but I can go do something else. It takes about as long as it does to make the lesson, like to actually speak it. If it's an hour lesson, maybe it takes an hour and a half to 2 hours to actually make it, including the editing and the setting it up.
Oh, that's not that bad.
It's not that bad. It's not that bad. Final Cut Pro makes it really easy because it syncs up the sound already, and then I can just sort of have them all together in a glom, and I can play it, and then you have all the different video tracks and soundtracks, and I can click on which one I want to appear at what time, right? So it's like, okay, I want wide view, click, and it goes to wide. It's like screen view, screen,
Yeah.
right? So I can just, it works.
Okay.
Okay, so circular motion, very briefly.
Oh, circular motioning is
Yeah, I know it comes back. Okay, so here, why don't we assume, and I'm not going to do the calculations for this, so you'll forgive me. So why don't we have a vector here? The velocity is initially this way. And then why don't we say all these dots are magnetic fields like out of the page? Okay?
Out of the thing?
Out of the page. I won't, you don't always have to draw circles, right? Okay. And why don't I say fingers out of the page, thumb out of the page to the right. So why don't we say it's a positive charge? Out of the page. And then that way, yeah, so why don't we say it's a positive charge? One of the things that's hard about this is that I have to refer, if I'm referring to you with the computer screen in front of me, I have to refer to that physical screen and not what's in front of me to make it make sense to you, because mine is reversed. So this is learning how to teach without moving to the screen. Okay, so what we say here is, okay, and then there's still B's here. Okay, so if these are B's right here, yes, we have like out of the page, so out of the screen, yes, and then the velocity that way. So which way is the force? Down. So the force is down at that point. So the force is down. Let's do it neatly. Just make it a little bit of a short one. So that's F. And now if the force is down, that it accelerates it this way. So it's now there. And then the velocity would be, say, that way. Whoops. That's not what I wanted. It's that one that I wanted. So now the V is the same V, same speed. But now look at it. Which way, you tell me, which way does the force go on it now? Yeah?
Is it like here?
Out of the page, and then, okay, I just want to make sure I'm right here. Okay, so out of the page, like that, and like that, yes. So V is sort of, the force is that way, yes?
Just to make sure of the reason why like the acceleration is going this way, because why is the acceleration is going this way after?
Well, think of it like a hockey puck going to your right, and then I apply a force. Swat. The slap is the force. Okay, so it's going this way.
Mm-hmm.
Yes, slap.
Oh, once it enters the magnetic field, there is like immediately.
Yeah, we'll assume the magnetic field is everywhere here. Okay, it's wide. So think about so it's first going to the right, and then force, boop, and then force going, boop, and then boop. Yes, and it's always perpendicular to the velocity.
Oh.
I should have mentioned that. That was the thing. That was the thing that I forgot to mention as well. The force is always perpendicular to B and V. So the force,
Yeah.
F.
Because it's like third dimensional.
Yes, F is perpendicular to B and V at the same time. Yes, that's why we have the plane, right? The plane ensures perpendicular to both vectors at the same time. It's a way of visualizing. the perpendicular force. It's perpendicular to both. So what we end up getting here then is that it goes in a circle. So when it's here, the velocity is down that way, and then the force is this way. And it's always the same magnitude force, and it's always the same magnitude velocity. Yes. And then over here, again, velocity, and then FB is your force. And then here, the velocity is this way, and then the B is that way. So you can clearly see that there is a center-seeking, a centripetal force acting on the charged object, which is, of course, positive, right? Yes, it's a positive charge moving. So we have V, FB, V, FB. You get the point, right? Okay. So it goes in a circle with a. And it has a. You can calculate the radius of the circle. There's an R. And we set it up with this MAC equals sum of forces. I won't get numbers on this. I won't put numbers into this. But we have mv squared over r, if you'll remember, is equal to FB. This is equal to FB. And that is equal to QVB. Yes?
Also, like, combine two of them.
Yes, we do.
So, the M is the mass of the charge.
Yes. Yeah, so it could be like a proton, for example, if it's positive charge. So
it's like really, really, really light.
yeah, small. But the electrostatic force is quite large. So it'll go in a circle. And we could, of course, so mv squared over r is equal to qvb. Okay. We can even set up an equation for the period as well. If it's going in a circle, you could tell it's like the period of one circle, like 2 pi r over t. But I won't get into that right now. But that's where this could go. But of course, we could solve it as being this. We could solve it as being mv squared over qb. Yeah, and that's the radius it travels at.
Wait, so would it be like
So this is the centripetal acceleration,
right,
v squared over r.
right, and then you divide it by, so it's like mv squared over qvb, and then you cancel these out.
I put the r up, and then the qb goes. Oh, I should have. Oh, that was. I knew there was a. There.
Yeah.
Should be a v down there, and it cancels, which is equal to mv over qb. I thought that square looked a little bit out of place because I was being a little bit sloppy there. Okay, so mv over qb. And yeah, so we could take it. You could take it from there. You can do quite a lot with this. The next topic after this, which I doubt I would be able to get into meaningfully, is this idea of flux, magnetic flux, and how changing the magnetic field inside a loop causes a voltage, like a current, to flow. Yeah.
It's all connecting together.
Oh yeah, it's at the end. It's the most conceptually challenging chapter of the year, in honesty. Although relativity was kind of weird too.
Yeah,
But-
relatively. So weird.
I know. Yeah, I like the new curriculum where we're bringing relativity into it. It so belongs in grade 12, special relativity.
It wasn't there.
It used to be in grade 11. It used to be this sort of nice little enrichy thing to make students go ooh and ah after they'd finished the energy. But now it actually interacts with the whole course, right?
Because like these are all using special relativity.
Yep. Magnetism and special relativity. And even we used to do relativity, like just vector relativity, but we never mentioned Einstein in grade 12. So you remember relative velocities? You know, like what's the velocity of a boat relative to me?
Relative to the other one.
Yeah, relative to the air, relative to the water, and so on. We used to do that. That's always been in grade 12. But I love it now that they put special relativity into the same course, because that goes with the, you know, the sailboat problems in a way. Yeah, so it goes. It's a good course right now. I'm happy with the change. Anyway, I should stop before it fills up my whole hard drive.